Hello all, and welcome back to video 3 of my 19-part YouTube series on simple machines. Machines and anything else I feel like talking about for 19 lessons. This one we're going to focus on levers. Figured it'd be a good start. Good part of the 19. We talked about on Monday that a lever is a rigid rod that rotates around a fixed point, the fixed point being the fulcrum. In the demonstration that we did in class, I had people try and open the door from different distances away from the hinge. The closer you were to the hinge, right, when you pushed, the more difficult it was to move the door, but the less distance you had to do to open it. The further you were away from the hinge, the easier it was to move the door, but the further you had to move the door. So let's take a look at a little drawing here. We've got to do some definitions. In every lever system, you have three components that you're going to need to identify. The fulcrum, which is the point of pivoting or the point of rotation. Okay, so our fulcrum in black here. Let's take a gander. Our fulcrum in black is this spot right there. Okay, great, fantastic. All right, and then the force applied to the lever. Interesting. The force being applied to the lever, this is your effort in green, so we'll come over here. Our effort is being pulled down like that, so we have force being applied this direction. And then in yellow, we have load, obviously, over here. So you need to identify these three components, and this is how so the load is the thing that's being lifted or the thing that is being moved, and sometimes it's not always as simple as a box or a weight. Like a door, the weight is kind of continuous throughout, right? Your effort is where you are applying that force. That's the human aspect, fulcrum being the pivot point. So the longer you make the distance between the effort and the fulcrum, the easier it is for you to lift the object, basically. Like I said, I'll say Archimedes' line once more time. If you give me a fulcrum and a lever long enough, I'll lift the earth. As long as you made it long enough and you can make it sturdy enough. Okay, next slide. Here we go. We're going to go over the three classes of levers and kind of how to identify them and what to look for. A first class lever is when you have the fulcrum in between the load and the effort. So I would be applying with my hand, pushing down here on the lever, and then it's pivoting around this point here, and the load is what's being lifted is also pushing down. So I have to overcome the force I apply here is going to have to overcome lifting up the load on the other side. So first class lever is when the fulcrum is between the effort and the load. So take a look at these two items here. Let's go ahead and identify. I'm going to say my fulcrum. So let's do the fulcrum. I think what was the color we used last time? Fulcrum was black, green was effort, yellow was the load. Okay, so let's take a look. Fulcrum in black. The point of rotation, clearly that's going to be this spot right here. Your effort, that was the thing that was green. So effort is where you're going to be clipping. I would imagine to create the most effort, you'd be clipping somewhere or grabbing somewhere around here. And the load is the thing that you're trying to act upon using your leverage. And you could be out here, you could be out here, but anyone who knows that when you use scissors or shears or tree snippers, the closer you get to the fulcrum, the more power you have. So let's assume we're cutting something that's right about here. All right, so there you have your effort arm, so your effort, your fulcrum, and your load. Identified, the fulcrum being in between them. The hammer is not as straightforward. Your fulcrum or point of rotation kind of depends upon where your hammer is. Based on this drawing, it's right here, but usually it would be up on the tip of your hammer depending on where the nail is as well. So there's our point of rotation. The load is the thing that's being moved. That would be the nail right here. And our effort is our hand going this direction. So we can identify those. And as you can see, if you follow down this arm or down the lever, fulcrum is between the load and the effort. First class levers are your classic teeter-totter situations. You got something on one side, something on the other side, and you could call one the rod and Todd. You could call rod the load and Todd the effort, or vice versa. Okay. So, anyways, that's the first class. We're going to do some calculations with it in just a sec. On to class number 2, which is the second class lever. Real quick, let's think. Can you think of anything else that's a first class lever? Try and pause the video for a sec and see how many things you guys can name. So maybe write them on the board and see how many you can get, and check back and see what comes up. Moving on to second class here in a sec. Second class lever is identified a little bit differently. In this situation, you have the fulcrum, the load, and the effort. And in this case, the fulcrum, the load is between the fulcrum and the effort. And the most common ones, there are multiple kinds. Most common ones I could think of here were a wheelbarrow and a nutcracker. So typically, the load is placed between the fulcrum and the effort here. So pretty clear to see. Let's go through and identify each. Where's the fulcrum? In this case, the fulcrum in black is right here. My load is in the wheelbarrow, and on average, the center of mass is probably somewhere right around here. And the effort, where we're pushing back, is right here. Okay, so pushing back, you get your fulcrum, so on and so forth. Let's go through, do the fulcrum here, point of rotation. Looks like that's going to kind of have two levers working together here in this nutcracker situation. And let's see, and then in green we have our effort. It kind of just depends on where we're grabbing. Probably grab, let's say, right around here. Okay, there we have our effort, and the load is what's pushing back up against the objects. So there's our load, which is the nut. And yeah, I think that's a pretty good example. We're going to come back and we'll label the effort arms and load arms here in just a minute. Okay, so let's go ahead and move on to class number 3. Okay, so this guy needs a third class lever. If you said tweezers, you were correct. Man, he needs tweezers and maybe some other things to solve his problems. Holy mackerel. Moving on. Third class lever. This is where you have the effort between the load and the fulcrum. Now, notice how many class of levers are there going to be, right? You have three things: the load, the effort, and the fulcrum, right? Those are your only options. And how many ways can you order that? Well, if you were to switch these, if there's 3 things, basically only one thing can be in the middle at once. There's going to be 3 classes. So this is the last of the 3 classes of levers, since only one thing can be in the middle at once. So the first class, we had the fulcrum in the middle. The second class, we had the load in the middle. And the third class, you have the effort in the middle. Fishing pole, same deal. Effort between the load and the fulcrum. So let's take a look. With this fishing pole scenario, the fulcrum is where this is placed into the sand. The effort is, or the load is actually right here, pulling this direction, obviously. And the effort is what is pushing back. So they're opposing, the load and the effort are opposing in this situation. Yeah, so that's third class lever. And you guys jot down, make sure you jot down a picture of these and write down their definitions as well. Okay, so that's class lever number 3. Here are some other examples. Let's go through. When you're paddling, well, it kind of just depends. When I use a rake, we'll go ahead and call, technically your hands are working in conjunction. That would be your fulcrum maybe. Your load is down here. What you're raking, it's pushing back against your rake. So is the ground. And your effort is swinging over this way. Okay. So we're going to come back and we're going to revisit each of these pictures in just a second. First, next I'm going to teach you how to calculate the mechanical advantage for each and how that kind of works and makes sense. So mechanical advantage is always going to be equal to your effort arm, we're going to do effort arm in green. So your effort arm divided by your load arm, which is this right here. That's going to give you your mechanical advantage. So the effort arm is the distance between your effort and the fulcrum. The load arm is the distance between the load and the fulcrum. So let's go through each one of these. Distance between the load and the fulcrum here is that line right there. Let's do this one. Load and the fulcrum right here. And last one, load and fulcrum, third class. Yikes. Yep, that's got a long stretch. Okay, and in green, distance between the effort and the fulcrum. Okay, effort and fulcrum. Look at this. That's got the long one, and effort and fulcrum. So notice since it's effort arm divided by load arm, in two of these situations, the mechanical advantage is in your favor. And what I mean by that is you have a mechanical advantage that's greater than 1, which makes things easy to lift, easier, rather. You're applying less force. And in one situation, it's actually harder. We'll go over why that might be. So in this one, since your effort arm is longer than your load arm, this is going to have a mechanical advantage that is MA is greater than 1. This one right here, again, effort arm, the distance between the fulcrum and the effort is longer than between the load and the fulcrum. So in this case, your mechanical advantage is also greater than 1. Okay, and then down here, your load arm is longer, which means you have a mechanical advantage that is less than 1. And that doesn't necessarily mean that that's bad. It just means you are using the tool differently. So let's go over the kind of the positives and negatives of each one. If you have a mechanical advantage that is greater than 1, that means the work is easier, but it's slower. Okay, so let's go back to those situations. Mechanical advantage greater than 1, first class levers. Okay, I'm fine with it being easier to trim through trees because that's something that I can't do with my bare hands, right? I can't pull a nail out with my bare hands, so I'm fine in it taking a long time to do that because I have more power to do it. Absolutely, absolutely, okay? Second class lever was the same, wheelbarrow. The effort arm, right, the distance between our effort and the fulcrum, and our load arm, the distance between the load and the fulcrum, this one was bigger. So this is providing us a mechanical advantage, which makes it so the work is easier, but it's going to take longer. So the longer I made these handles, the higher I would have to lift them to get the feet off the ground, right? That's kind of the idea. But it's not terribly bad. All right, here. So let's see. Moving on, let's go down and take a look at third class lever. Now, in this case, remember your third class lever was, let's do the effort arm and load arm here. So it looks like our load arm from the distance from the fulcrum is going to be, well, before it was flexed, it would have been this long distance here, and our effort arm was the distance here. So in this case, when you have something like this, or like a set of tweezers, it's allowing you to be more dexterous. You can make a minute movement with your effort, and it will have a great movement here. So because you have to apply more force, you're moving less distance, basically. You're lifting something that's light. You're not using this pull to lift something terribly heavy or heavier than you. And so what this is doing is it's allowing you to make the work harder, but you can bring the fish in further at a time, right? So you can move your hand 6 inches, even though it's harder than lifting from out here. It's easier to lift out here to lift the fish. But when you move your arm 6 inches here, you're actually bringing the fish in a couple feet. So it makes it faster. So you're sacrificing the difficulty or the force required for being able to make the job faster, which is what that last comment was. Okay, if you have a mechanical advantage equal to 1, in other words, if you were if you made your hammer, like if you were to reach over here and you were to apply your effort on this side of the hammer, it'd be the same or the same difficulty as trying to pull it out with your bare hands. You're not providing any mechanical advantage, but because you're grasping up here, right? So mechanical advantage equal to 1 has really no effect on alleviating work. You're just changing the way you're applying the force. Less than 1 means the work is harder to do, but it's faster. And the perfect example I can think of for less than 1 or a third-class lever is like a broom or a rake. This is not a terribly heavy object, a broom or a rake. It's not terribly heavy to lift. And so what that means is you can grab here and move the rake very quickly, much faster than you can move your hand, right? You can move this much faster, just like a person playing badminton can you move their racket much faster than if they were to try and move their hand to grab something. So because you have this extension, the amount of force required is a lot greater than using just your hand or maybe grabbing the rake down at the base. However, you're able to whip that thing around a lot faster. So there's our effort arm, and here's our load arm. Third-class levers do have a use. They make work harder, but faster. Perfect. All right, I think that's about it. Oh, let's do some calculations. And actually, yeah, let's do some practice calculations here. So with this situation, I'm going to identify where each of these is. I'm calling this point my fulcrum. I'm going to call this point here my load, and I'm going to call, maybe I'm grabbing these right about here for my effort. Let's calculate mechanical advantage, do some practice calculations. So you, on your assignment, basically what you're going to label is this a first, second class. These are a second class lever, so you'll spell out this is second class. We've gone over that already, so make sure you spell that out on your assignment. Second class lever, I need to find my load arm, so you're going to grab some rulers from the back of the classroom. They're by the calculators. So the first thing I'm going to do is measure my load arm, how far my load is away from my fulcrum. I'm going to use just a ruler on my screen. As long as I don't zoom in, it shouldn't matter. It looks like about 2.4 centimeters. I'm just kind of estimating here. The load arm was measuring from this point to the fulcrum, and I got, yikes, 2.4 centimeters. My effort arm measuring from my effort, which would be the force pushing on these grippers, right about here. That is measuring with my ruler. Looks like about 6.3. So come over here, label my effort arm as 6.3 centimeters, which means I can now calculate my mechanical advantage. Mechanical advantage is equal to input divided by output, right? Effort is my input, input divided by output. So you do 6.3 input divided by output, 2.4, which gives me a mechanical advantage of, drumroll please, mechanical advantage of 2.63 roughly. So that means using this, it's about 2.63 times easier, or less force needs to be applied to the system, but I have to move it 2.63 times further to do so. Great, next one. The shears, let's say I'm going to identify my fulcrum as this, the nut and bolt here. My load is going to be the thing that I'm cutting in my scissors, and my effort is going to be where I'm grabbing this, and I'm going to call that, by the time it's straightened out, I'm going to call it right about here when they swing in, okay? So let's go ahead and measure this out and calculate mechanical advantage. This is a first class lever. The effort arm, let's do that. The effort arm is measuring with my ruler in centimeters, just fine. You guys are just going to use And on the assignment, there's some arrows. You might actually have to draw in those points yourself. I just have them pointing to. You're going to label which one's the load and which one's the effort. So on your assignment, you'll come over here and you'll say, this is the load on each arrow, this is the effort, so on and so forth. So load, effort, and fulcrum. So you'll have to do that as well. Effort arm, I'm measuring. Effort to the fulcrum looks like it's about 4.3. 4.3 centimeters. The load is about 1.3. Load arm is 1.3. So LA, 1.3 centimeters. And now calculating mechanical advantage. MA is equal to effort divided by load, which gives me 4.3 divided by 1.3, which is a mechanical advantage of 3.31. Not bad. Okay, cool beans. Now, some of the times, remember, you will get a mechanical advantage if you're doing stuff with third-class levers that is less than 1. So third class should always be less than 1. Second and first class don't necessarily have to be greater than 1, but they usually are. And I think that'll do it. So you guys have the rest of the time to work on that worksheet there. Make sure you're showing your work for each calculation. And please draw in the points you're using to measure. So thanks for the hard work. Hope you guys learned something today. Have a great day.